Welcome to our next Djji tutorial session. Today we are discussing laws of exponents for rationals and applications of rational exponents. Exponents and radicals are related because radicals can be expressed as rational exponents and vice versa. A radical, like a square root, indicates taking a root of a number, while exponents indicate repeated multiplication of a base. Here's a more detailed explanation. Radicals as rational exponents, square roots. The square root of a number, for example, the square root of x is the same as x raised to the power of 1/2. Cube roots, the cube root of a number, for instance, the cube root of x is the same as x raised to the power of 1/3. In general, the nth root of a number, such as the nth root of x, is the same as x raised to the power of 1 over n. Rational exponents as radicals. X raised to the power of 1/2. This means the square root of x. X raised to the power of 1/3. This means the cube root of x. X raised to the power of 1 over n. This means the nth root of x. More complex cases. When you have an expression like x to the power of m divided by n, m is the power and n is the root. This can be written as the nth root of x raised to the nth power, or as the nth root of x, all raised to the nth power. For example, the radical cube root of 8 can be written as a rational exponent, 8 to the power of 1/3. Similarly, the rational exponent 9 to the power of 1/2 can be written as a radical, the square root of 9. In essence, understanding the relationship between exponents and radicals allows you to convert between these two forms, which can be really helpful in simplifying expressions and solving equations. What you're solving for is simplifying an expression with exponents and radicals. What's given in the problem is the expression 8x to the 6th power times the square root of 8x to the 6th power multiplied by the fraction with numerator 1 and denominator x squared. Helpful information includes the properties of radicals. The nth root of a times b equals the nth root of a times the nth root of b. Also, the properties of exponents. A to the nth power times a to the nth power equals a raised to the power of m plus n. And the fraction with numerator 1 and denominator a to the nth power equals a raised to the negative n power. How to solve? Simplify the expression by using the properties of radicals and exponents. Step 1. Simplify the radical. Rewrite the expression with exponents. The square root of 8x to the 6th power end root center dot the fraction with numerator 1 and denominator x squared n fraction equals open paren 8x to the 6th power, close paren raised to the 1/3 power center dot x to the negative 2 power. Now simplify the radical. The square root of 8x to the 6th power end root equals the square root of 8 end root center dot the square root of x to the 6th power end root equals 2 center dot x, raised to the 6/3 power equals 2x squared. Substitute back into the expression, 2x squared center dot the fraction with numerator 1 and denominator x squared n fraction equals 2x squared center dot x to the negative 2 power. Step 2, simplify the expression with exponents. Use the property a to the mth power center dot a to the nth power equals a raised to the m plus n power. So 2x squared center dot x to the negative 2 power equals 2x raised to the 2 plus open paren negative 2 close paren power equals 2x to the 0 power. Simplify the exponent. 2x to the 0 power equals 2 center dot 1. Step 3, final answer. The simplified expression is 2. So the solution to our problem is the simplified expression, which is 11. Rational exponents, which represent fractional powers, have diverse applications in mathematics, science, and engineering. They are crucial for simplifying expressions, solving equations, and modeling various real-world phenomena. Specifically, they are used in physics to calculate electrical resistance and wave frequencies, in finance to model compound interest, and in engineering to analyze structures and processes involving fractional powers or roots. Here's a more detailed look at their applications in mathematics. First, simplifying expressions. Rational exponents allow for a more concise and efficient representation of radicals, making it easier to manipulate and simplify expressions. Second, solving equations. They are essential in solving equations where variables are raised to fractional powers, often requiring the use of properties of exponents to isolate the variable. And third, calculus. Rational exponents are frequently used in calculus, especially when dealing with derivatives and integrals involving radical functions. In the realm of science, rational exponents find numerous applications. Let's start with physics. Rational exponents are applied in calculating electrical resistance, wave frequencies, and other physical quantities involving fractional powers. They are also used to model radioactive decay and other natural phenomena. Moving on to biology, in population growth and decay models, rational exponents are used to represent the exponential relationship between time and population size. These applications, well, they highlight the versatility and importance of rational exponents in scientific disciplines. Engineering, structural engineering. Rational exponents can be applied in analyzing the strength and stability of structures, especially when dealing with fractional powers related to stresses and strains. Material science. They are used in calculations related to material properties, such as conductivity and elasticity, which may involve fractional exponents. Finance, compound interest. Rational exponents are used to model compound interest calculations, where the interest earned is calculated based on the principal and the number of compounding periods. Investment analysis. They can be used to analyze investment growth and calculate returns over time, especially when dealing with fractional periods or compounding frequencies. In essence, rational exponents provide a bridge between exponentiation and root operations, enabling efficient manipulation of expressions, solving complex equations, and modeling real-world phenomena in various fields. We hope you found this session useful and share it with your classmates. See you in the next session.